Theodosius Dobzhansky, who said, nothing in biology makes sense except in the light of evolution. I think he's absolutely right. There's so many things that just are weird or, convoluted. And we think they're natural, but it's really not. It's really not. And I think it really organizes our understanding. It's kind of like, evolution is kind of like the grand unifying theory of biology. And to me, it's actually kind of strange that everybody isn't doing this. Everybody isn't reading about it all the time and using that. It seems like kind of necessary. And I think, the reason, so there's the personal reason that I just find it so interesting, right?
Which is good
but
enough.
Then there's a sort of a practical reason, and that is that a lot of things in neuroscience don't make sense, exactly as Dobzhansky said. And people are trying to understand them, and I'm one of those people trying to understand them. But a lot of it has to do, a lot of the answers, I think, lie far in the past, and can't be seen, can't be understood until we look at that past. So, for example, there's a lot of studies in psychology that ask, how does the human brain work? And there's certain questions and certain answers that come up along the way, but they're just not really working out. I mean,
right.
I think there's this feeling that, neuroscience is progressing so fast, but we're actually still struggling with some of the same questions we were struggling with 100 years ago. And I think part of the reason is that we're looking at it from the wrong end, right? We're looking at it as if the human brain was, optimally designed to do the kinds of things that we care about.
Right.
And I don't mean that we do, because we do lots of things, but the things that we are most impressed by are the kinds of sort of, cognitive abilities that we really excel at. Things like a conversation that we're having right now. That just seems so impressive to us. We want to understand it, right? But it's not working out. And I think the reason it's not working out is because when you look at the brain, a lot of it is actually organized around the kinds of tasks that have nothing to do with the kinds of things we use them for now, right? And I think everybody knows this, right? Everybody says this all the time, right? But I think once you really take that seriously, and you ask yourself, well, are we asking the right questions?
Right.
Then it's obvious that the answer is no. That we have to ask questions in a more sort of biologically fundamental way first, before we can go and ask about, human cognition.
What do you think is
that's a practical reason that everything that I do in the lab and in my sort of day job is enlightened, I think, by all this work that other people are doing, looking at many different animals and trying to draw comparisons and inferences about what those ancestors were like. And I think by reading their work, I'm understanding everything that I do much more clearly.
Absolutely. That makes complete sense. What do you think is one of the best concrete examples of that, where looking back in our evolutionary past has informed a mechanism that we understand today?
Well, I think one of the biggest things, the most important thing is, to me at least, is that, we think often in psychology that the brain is an information processing system. It's like a computer. It takes inputs and it does a lot of computation, and then it produces outputs. And from that perspective, there's a certain number of questions that you might ask about how it represents information, et cetera, et cetera. But when you look at evolution, you realize that's completely incorrect, in fact, because the brain is really a control system. And you realize that everything in biology is actually essentially a feedback control system, a series of nested and complicated interacting feedback control systems. And behavior is not an input-output process because it's a closed loop, right? The output creates new input. And you're not, in natural behavior, it's not like you are in a psychology experiment where you're presented with a stimulus and you produce a response, and you are then rewarded if it's the right response, and then you try again from scratch, right? That's how we've been studying the brain. And when I
Right.
say we, I mean me, myself as well. But that's not what animals are doing. What animals are actually doing is controlling their state. They're controlling their state to make sure that they're fed, safe, warm, etc. And life and the behavior essentially is a process of transitioning between states by knowing how your output affects your input. So you're essentially continuously controlling the state, your state in the world and internally through output that you emit through the environment, and you choose the output so that the input, which again informs you about what state you're in, is telling you that things are good. So for example, I'm not being threatened. To not be threatened, the things you do, there are certain things that you do, such as move away from predators. And if I'm hungry internally, then I go out and seek food to control that state. And, this is, of course, trivial. But what is, I think, not appreciated is how accepting that trivial observation changes completely the even kinds of questions that we ask about how the brain works and what it's actually doing. Right? It's not about producing responses or building knowledge inside the head. That's a useful means to an end, but the end is control, right? And so that is, I think, the most important thing that you realize. I mean, you don't need to look at evolution to realize that, but I think when you look at evolution, you realize it's a story of expanding control systems in every case, and humans are no exception. Even the kinds of things that we do, even the kinds of conversations we're having, are essentially embedded within this kind of control system.
Right.
So that's the
I think.
biggest. I mean, there's specific examples I can give. Like, for example, why do the receptors in the retina point backwards? This is my favorite example because it's so well known that our retina, the receptors are pointing backwards. And there's a lot of attempts to explain this on the basis of like optimality, that maybe it does some filtering, noise filtering, or maybe it protects in some way. But it has nothing to do with that, actually. The answer is very simple, and it has to do with what happened in early chordates, where the nervous system sort of folded inward into a tube. And it essentially drove the receptors that were originally pointing outward, sensibly pointing outward, got folded inward with the creation of the neural tube, something like 800 million years ago. But it didn't matter because the animals at that time were like a millimeter in size and completely transparent. And the only thing they did with those photosensitive cells was like control circadian rhythms, or maybe escape from a shadow or something, right? But once they got folded in like that, there was no going back. And then when the eyes formed, they sort of migrated to the sides of the head with the receptors still pointing inward, created, the retina and the lens and everything. And it was just impossible to flip them over, to flip them back out. So now we have incredibly visually acute animals like hawks and humans and cats that have this ridiculous backwards retina. And it had to do with something that happened long ago. Whereas octopus has the retina facing, the receptors facing the sensible way, right? Because it never went through that stage. It developed an eye through many of the same kinds of, evolutionary adaptations. It's actually quite similar to ours, but it's not backwards. And again, it has to do with the history. And there's lots of examples of this that are maybe a little bit more unfamiliar about things that happened, along the long road that we took.
That's a beautiful one. That's a really, really cool one. Dr. Paul Cisek, what an absolute goldmine of information. If you enjoyed that short clip, then I'm so confident you're going to enjoy our full 2-hour-long conversation, which basically covers the entire evolution of the human brain. You just have to click it here. You can click it right now, here.